I have one more problem to do, and actually as I was getting ready for today's lecture, I'm not real thrilled about how my slides look. This is a problem new to this semester for me, and so actually I'm going to work the problem either with my stylus on the Surface Pro or over there. My stylus doesn't work. But the thing about thermodynamic problems is they come in so many varieties. And they're story problems, and some people hate story problems. Some people love them. But the thing about story problems is I like oftentimes a picture can go along with it and kind of help tell the story. So let's see, I've got 52 grams. These are my ice cubes. So 52.0 grams of H2O in its solid state. And they, by the way, their initial temperature is cold. Negative 12 degrees Celsius. Of course, they're below the freezing point of 0 degrees Celsius, which makes sense. And I am going to go ahead and dump them in a beaker of water. And it tells me that the mass of that water is 133.0 grams of H2O in its liquid state. And the temperature here, initial temperature of the water, is 22.0 degrees Celsius. So just intuitively, before I go to the last sentence, which is a question, does this make sense that you figure those ice cubes are going to melt, and you're right. Okay. Here in a minute, we're going to end up actually with 3 Qs that kind of are what's going on here. And so, make sure I kind of stay with the same. We're going to have a thermal energy Q associated with the ice melting. But before the ice can melt, does this make sense? We're below freezing. So before it can melt, actually we're going to take the ice and it's going to go from negative 12, it's going to bump up to 0. So that's a different Q. And we're going to be calling that Q of warm ice. Q of the warm ice. What that means, like I said, is it's going from negative 12 to 0. And then it's going to melt, go from a solid to a liquid state. But you figure we have something else going on. And in all of this, if you had a thermometer in this water here, this 133 grams of water, you'd probably tell me the thermometer would go up. That water would get colder. And that's our third thing going on. So we're going to call that Q of, I think I just have here, Q of liquid water. More descriptive probably would be what? Cool water. Same thing. So these are the 3 things that are happening when I take my ice and put it in my liquid water. So those 3 things are in my system. So Q of my system are those 3 things that are going on. My Q of my system, hopefully we're all on the same page. That's if it's isolated, the change in energy of my system overall is 0. So on a test, I would, oh, sorry, there's no question. Now, the question is, what mass of ice will need to melt in order for that water to cool down from 22 to 0? So wow, you're going to take the water that's definitely above freezing and you're going to cool it down right to the freezing point with transition. So that's the question. So I'll show you how that mass enters in here in a minute. Things that you would need for me to work this problem, hopefully, actually you don't need this from me. Can you guys tell me what this temperature is? It is 0 degrees Celsius. What is this specific heat of liquid water? That was off the tip of your tongue.
4.184.
4.184 joules per gram degree Celsius. Perfect. Now you wouldn't need to know this specific heat. Okay, this is the specific heat of that ice cube as it. We're going to use that as we cool down from negative 12 to 0. Do you need to memorize this one? Nope. That's the energy that will be required to melt 1 gram of ice. It's going to require 330 joules. So let's see if this will, looks like it's working pretty good. So I'm going to kind of redo this a little bit. The problem statement. The mass of the water was 133 grams. And the mass of the ice. So this would suggest that not all 52 grams of that's going to have to melt. 52.0 grams H2O solid. And I talked a minute ago that what's going on in your system, Q of the system, we have 3 things. We have, and let's just go in order. We have the Q associated with, I'll go ahead and put T sub I. We said that's a chilly temperature. Your ice is negative 12 degrees Celsius. So there's that Q. We'll call it Q of melt ice plus Q of the, oh, darn it. I suppose. Wonder I can't go backwards. Q of melt ice, I kind of got ahead of myself. Before that, we need the Q of the ice warm. What do I call it? Warm ice, I guess I call it my slides. And then these would be what? See, would they be endo or exothermic? I'm thinking endo. Endothermic? And then we have the water cooling down. So Q of, I have here just liquid water. Or you could put water cool. And if it's isolated, those 3 Qs are 0. So does this make sense that to do the melting, and we did this, an example of this in class on, this is Wednesday, on Monday, to deal with the thermal energy required to melt, we're going to do what? That Q is equal to mass times the heat of fusion. Make sense? For these 2 Qs over here, for either our ice cube warming up to 0 degrees Celsius or our water cooling down to 0 degrees Celsius, for both of these, we're going to use Q is equal to the mass that's either warming or cooling times the specific heat of the ice or the water times the change in temperature it will undergo. So that's kind of it. We had some, I'll go ahead and kind of make this like a natural sort of barrier. We know some things about the solid and we know some things about the liquid. With regard to specific heat, C sub P of liquid, C sub P of the solid, I would give to you, that's that 2.06 joules per gram degrees Celsius. The specific heat of water, liquid water, you would tell me is 4.184 joules per gram degrees Celsius. Our delta T's, we can go ahead and knock those out if that's okay with you. The delta T of our solid, it's always final minus initial. So it's, the final is 0 and the initial is negative 12. So if I take 0 minus negative 12, I get 12. Our delta T on the liquid water, let's see, it's always final minus initial. So my final is 0 and my initial is, I didn't put on my slide, but the initial was 22.0 degrees. So I'm liking
Dang it, I'm like in negative 22.0 degrees C. That all works. So let's take a look at the phase change part of it. Let me go ahead and kind of make a T out of my work area up here. The phase change part of it, the Q required, like I said, is going to be equal to the mass of the ice that melts times the heat of fusion. Heat of fusion, or melting, same thing. Which we were given in we're given heat of fusion. So remember that the mass is my thing I'm after. So I'm going to go ahead and put a question mark there, and go ahead and bring in my heat of fusion is that 333 joules per gram. Looks like a mess, a jumbled mess. I'm going to go on to the next slide because I'm kind of running out of room. But on the next slide, what you're going to see is to kind of bring together, and it's going to look something kind of like, I'm going to revisit this up here. So Q of the system, which is 0, is equal to the energy change associated with melting, and that's the mass, which is unknown. The heat of fusion, which was that 333 joules per gram, plus, now we get to our change in energy of the ice and change in energy of the water as the ice cools as the ice warms and the water cools. So Q is always mass, specific heat, change in temperature. So the mass of the ice, that's also a variable. Is the whole thing? No, that mass is not a variable. That mass is all going to come down to the equilibrium temperature. That mass is 52.0 grams. This is my solid ice. My specific heat of ice is 2.06 joules per gram degrees Celsius. Oops, sorry. And my delta T, we said, was 12. Cool. Goodness gracious. So I'm kind of running out of room there, but I need to add now my last Q, which is the energy associated with the warm water cooling down to 0. So the mass of that warm water is 133.0 grams. The specific heat of water as it cools is that 4.184 joules per gram degrees Celsius. And the delta T is negative 22.0 degrees Celsius. Woo! So in all of this mess, I've only got the mass that is going to melt. The mass of the ice that's going to melt is my only variable. So I brought my handy dandy calculator. Feel free to click along with me if you want to. I think I probably would, I'm going to go ahead in my calculator and get these down to joules. So I got 0 is equal to mass, which is unknown, 333 joules per gram, plus 52 times 2.06 times 12. Let's go ahead and convert that, if you don't mind, to kilojoules. So 1 kilojoule over 1,000 joules. And give it, what, 2 sig figs? So I got 1.3 kilojoules. So for the last term, if I take 33, 133. That's better. The mass of the water, 133 times its specific heat of liquid water, 4.184, times the delta T, negative 22, divided by 1,000 to get it to kilojoules. I get, oops, and go with 3 sig figs. I'm liking negative 12.2 kilojoules. So I'm going to take my kilojoules and put them on the other side just because I can. So negative 12 plus 1.3 equals, I get negative 10.9. I bring it over there. I got 10.9 kilojoules is equal to, is equal to the mass, which we're after, times 333 joules per gram. So if I divide both sides by 333 joules per gram, but I have to kind of fix my kilojoules. Let's see, I'm going to go ahead and fix kilojoules over here on the right side. I almost said the product side. On the right side, I'm going to go ahead and take that times, let's see, 1,000 joules? Nope. 1 joules. 1 kilojoule, 1,000 joules. Sorry, final answer. So now I can rewrite this. I'll put a semicolon so I'll show you I'm not doing a run-on. So 10.9 kilojoules is equal to the mass, which was after, and I got what, 0.333 kilojoules per gram. Just how my brain works. I should have done this in my office. I hope this works out. So now I can get the mass by dividing both sides by 0.333 kilojoules per gram. So the mass is equal to 10.9 kilojoules divided by 0.333 kilojoules per gram. And we definitely run into this in working problems. Of course, units of kilojoules will cancel with units of inverse gram in the denominator. That gives me units of grams. So when I do that, we got more than 55. Something's going on. That makes sense? So, as far, I'm going to double check, see what my other slides say. But I hope that makes sense. I know it's a bit of rambling. But just within a system, you have to kind of track what's going on, and then you have to account for those goings-ons by one of the equations we talked about. So this is what I don't like about my slides. It doesn't, of course, you guys know that means absolute value of. I'm not real thrilled with how this reads. I mean, it makes sense. We have 2 things that are, let's see, heat coming in. We have 2 things that are exothermic, or 2 things that are endothermic, 1 thing that's exothermic. So basically, the energy change associated with warming the ice and melting the ice needs to be accounted for in the energy change associated with the water warming, or excuse me, the water cooling. So you're going to see some very similar things as to how we just worked it. We need to know what is the change in the liquid water, but I don't like the absolute value signs. I think you're fine in just keeping the sign with it. That's how I do my answer. So the absolute change in temperature is 22.03 Celsius. Final minus initial, which for otherwise it really should be a negative 22.03 Celsius because it's exothermic. So if we're trying to kind of talk magnitude of the change in energy associated with water, okay, we can take its mass, which we just did a little bit ago, times its specific heat, times the delta T. Our delta T was negative though, wasn't it? And give ourselves 3 sig figs. So you're looking at, and I didn't convert it to kilojoules here, but I could have. Is that the same value we got before? So this would be the amount of energy
What's that?
Yeah.
Okay, thank you. This would be the amount of energy that was given up as it cooled down. Okay, so if that is given up as it's cooled down, I really don't like my slides. I'm like, really? I followed it that way? If that was given up as it cools down, that's the energy taken in to do the two things we talked about. To melt the ice, some of it, hopefully 32 so many grams of ice, and also then to go ahead and take that negative 12 degrees Celsius ice and warm it up to the melting point temperature. So we're assuming the system is isolated, so this energy swap can happen. So we're going to use Q is equal to mc sub p delta T to track the change in thermal energy associated with the ice warming up. So this is looking at the ice warming up. Again, I wouldn't work with the absolute value. I would just kind of let the sign right along with the delta T. So we use the specific heat of solid ice, which was at 2.06 joules per gram degree Celsius. Here's the mass of the ice. We're going to assume, this is where I kind of paused a minute ago, we're going to assume that all of that ice is going to go ahead and warm up to the 0 degrees Celsius. So rounding to 3 sig figs, I get 1.29 times 10 to the third joules. So again, I don't like how I did this. So now we can go ahead and say this energy here was, you might recognize from the water cooling down. That's the energy given off when it cools down. And then these two terms are have to do with the endothermic processes. We came up with a value of, we rearranged this, by the way, to isolate the melt term and then plug in the ice warming term. So hopefully you recognize where these two values came from. Okay. This value is from the water cooling down, and this is from the ice warming up. Push. So when you do the math there, and I like what we did and converted it to kilojoules because those numbers are nice and small. I like them without the scientific notation. So this is the amount of energy that we have left to go ahead and melt your ice cube. So remember, if you're melting your ice cube, all you got to just do it. It's the mass times this is the time, not the heat. If you're melting, it's the mass times the heat of fusion. So this is the energy, and this is actually the inverse of the heat of fusion, which I'm not real thrilled about. So again, I like the way I showed you before. I don't like my slides, so I'll probably go ahead and fix that hopefully for next fall. Is this the same answer?
You had a different round off on the 1Q, 1 ice. Yeah, you have 1.3.
Okay, so it's close.
1.2. Yeah.
Thank you. Okay. So any questions about that? Yeah. So we're bumping up against another homework. So today is Wednesday. I think I told you guys, did I write about it, that I did all that homework this summer, like in various places throughout my vacation, like that you've looked at online, but I don't have Unit 4 and I don't have Unit 5 homework done at all. So, oh my gosh. So I get to sit down and do that. I like Unit 4 material. I'll go ahead and give you a heads up that Unit 4 you won't need a calculator for. Weird, I know. But that means it's like just one of these brain things. I like calculators, they are my friend. So, but, yep, so I'll try to get some homework done. Because on Friday, we're going to start Unit 4 lecture. No, we're not doing anything fun. No. So, tomorrow we have lab, and I don't mean to psych anybody out, but it should be a short one. If everything goes right, if there's no then it can be a short lab. It's very similar to the lab that you did last Thursday with the equipment. Okay, that's all I got.